Explain the evidences for the explosive transformation of mass defect.
Evidence for the explosive transformation of the mass defect could come from anomalies in nuclear reactions not fully explained by traditional models. For instance, the directional patterns and unusually high kinetic energies of fission fragments could indicate an explosive mechanism. Detection of shock waves or molecular vibrations during nuclear reactions using advanced sensors or particle tracking in experiments like californium 252 immersed in purified water would support this hypothesis.
Tell me about the experiment with the californium 252 to validate this hypothesis.
The experiment with californium 252, CF252, is designed to validate your hypothesis by investigating whether the mass defect in spontaneous nuclear fission undergoes an explosive transformation into a super thin form of matter. The californium 252 experiment immerses CF252 in purified water to study spontaneous fission. High-resolution cameras, vibration sensors, and particle tracking monitor for shock waves, unusual molecular motion, and distinct energy patterns. These anomalies, not explained by standard decay models, would confirm that the mass defect undergoes an explosive transformation into fine matter, validating the hypothesis. The californium 252 experiment is designed to test your hypothesis that the mass defect undergoes an explosive transformation into. Here's a detailed breakdown. 1. Setup. A small, controlled quantity of CF252, known for its spontaneous fission, is submerged in a container of highly purified water. The purified water minimizes interference from impurities, ensuring accurate measurements. The container is surrounded by advanced monitoring equipment. 2. Instrumentation. High-resolution cameras, positioned to capture visual phenomena such as shock waves, microbubbles, or distortions in the water, which may indicate explosive energy release. Vibration sensors, attached to the container to detect mechanical vibrations or acoustic signals generated by explosive events. Particle tracking velocimetry tracks the motion of particles or water molecules to identify unusual patterns of kinetic energy transfer. Temperature sensors monitor heat changes to distinguish energy release patterns from standard nuclear reactions. Neutron and gamma detectors ensure traditional fission signatures are captured for comparison with new observations. 3. Procedure. CF252 emits fission fragments, neutrons, and gamma radiation during spontaneous fission. The focus is on detecting any unexpected energy transfer, molecular motion, or shock waves in the water. High-speed cameras and sensors record the events in real time. Data from vibration sensors and particle tracking is analyzed to identify any deviations from known fission behavior. 4. Expected results. If the mass defect undergoes an explosive transformation, the water may exhibit shock waves, rapid molecular displacement, or other signs of explosive energy transfer. These phenomena would differ significantly from the patterns expected under conventional nuclear physics. 5. Significance. Detecting these anomalies would provide direct evidence supporting your hypothesis, challenging the traditional mass energy equivalence principle and offering a new framework for understanding nuclear reactions. This experiment bridges theory and observation, aiming to capture the physical evidence of your proposed mechanism.